When you think of ceramics, you probably think of something that's incredibly hard, right? Like ceramic armor that can stop a bullet, or maybe a kitchen knife that just never seems to get dull. But there's a catch. They have this reputation for being brittle, and what's really strange is how unpredictable they are. One piece can be unbelievably strong, but another one that looks exactly the same can shatter with no warning. So over the next few minutes, we're going to figure out exactly why this happens and, more importantly, how engineers have learned to master these amazing but kind of finicky materials.
Okay, let's just get right into the heart of the mystery. Why is a ceramic's strength so all over the place? I mean, seriously, how can you take two samples of the exact same high-tech ceramic and have one the almost 4 times stronger than the other? And this isn't just some weird science trivia. It's a massive challenge for engineers. Think about it. How are you supposed to design a reliable part for, say, a jet engine or a medical implant when the material's strength is basically a roll of the dice?
And this chart right here just lays the problem out perfectly. Take a look at alumina. That's a super common workhorse engineering ceramic. Now follow that row over to the transverse rupture strength. The members are just wild. They go from a low of 276 megapascals all the way up to over 1,000 for the same material. That huge scatter, that massive variation, that's exactly what we're here to unpack.
So, where on earth does this randomness come from? Well, the answer isn't in the material's chemistry. Nope. The answer is hiding in plain sight, in tiny, almost invisible imperfections that are lurking inside. And this is the most important concept to get your head around. A ceramic part is exactly like a chain, right? It doesn't matter if most of the links are super strong, the whole chain is only as strong as its single weakest link. And for a ceramic, that weak link is a microscopic flaw. And this is so cool, we can actually see the culprit. This is a micrograph, a super magnified image of a broken ceramic part. See that little dark spot right there in the middle? That is a tiny 50-micron void, smaller than the width of one of your hairs. And that single, insignificant-looking little spot is where the entire catastrophic failure of this whole part started. And these little troublemakers come in all shapes and sizes. They can be tiny pores, like little bubbles left over from the manufacturing process. Or they could be clumps of powder that never quite fuse together. Sometimes there are even microscopic cracks on the surface from grinding or polishing the part. Any one of these can act like a tiny stress magnet and become that one fatal weakest link. So the solution seems obvious, right? Just get rid of the flaws. And this graph shows exactly what happens when we do that. Each of those bell curves is like a different family of flaws. As we improve our process and knock them out one by one, moving from right to left here, you can see two things happen. Not only does the material's average strength get higher, but the curve gets tighter. It gets more predictable. And that's the real goal. But let's be real, making a perfectly flawless material every single time is pretty much impossible. So how do engineers deal with this built-in randomness? Well, they don't fight it, they tame it with the power of statistics. And this is where this really powerful tool called Weibull statistics comes into play. Now, don't worry, you don't need to be a math whiz. Just think of it as a special kind of language that's built on that whole weakest link idea. It lets us describe the flaws in a material and then predict the probability that a part is going to fail when you put it under a certain amount of stress. It's how we put a number on reliability.
This is what a classic Weibull plot looks like. And for an engineer, this is a beautiful thing. Let's just break it down real quick. The bottom axis is the amount of stress you're putting on the material. The further to the right you go, the harder you're pulling. The vertical axis is just the probability of it breaking. So you test a bunch of samples, you plot where each one breaks, and you get this characteristic line that tells you everything about that material's reliability. And the single most important part of this whole graph is its slope. We call it the Weibull modulus. Now, a really steep slope, that's what you want to see. That's fantastic. It means your flaws are all about the same size, which makes the material's strength super predictable. But a shallow slope, that's bad news. That means your material is a gamble. It has all sorts of different sized flaws, big and small, making its strength dangerously unreliable. So if you're designing that jet engine part, which slope are you going to choose? Yeah, the steep one, every single time. Okay, so to get the data to build these powerful charts, we need to break a lot of samples. So that brings us to the next question. How do scientists actually go about measuring the strength of these things in a controlled, repeatable way? You'd think you could just grab a ceramic bar and pull it apart, but it's not that simple. They're so stiff and brittle that if you're even slightly misaligned, it'll create weird bending forces and snap way too early.
it won't give you the true strength. So instead, we do the smart thing. We embrace the bending, and we control it precisely. The most common way to do this is with a bend test. And you'll often see the 4-point version of the test used instead of the 3-point one. And why is that? Well, it's all about statistics. The 4-point setup creates a bigger area on the bottom of the bar that's under the highest stress. By testing a larger volume of the material, you increase your chances of finding that single, critical, weakest link flaw. It's something we call the size effect, and it's why a big ceramic dinner plate is way more likely to break than a tiny chip made of the exact same material. More volume means more chances to find a flaw. Now, this is where things get really interesting. What happens if instead of pulling or bending a ceramic, you squeeze it? Look at these numbers. A ceramic can be anywhere from 4 to 30 times stronger when you compress it. So why the huge difference? Well, think about those little cracks. When you pull on them, you're basically prying them open. But when you push, you're squeezing them shut, which pretty much stops them from growing and causing the part to fail. Of course, there's more to a material's personality than just its breaking point. Scientists run a bunch of other key tests. They measure hardness, how well it resists being scratched, by pressing a tiny diamond pyramid into it. They also measure something called fracture toughness, which is absolutely crucial. That tells you how good the material is at stopping a crack from growing after it's already started. And there's even this weird phenomenon called static fatigue, where some ceramics, especially glass, can just fail over time while sitting under a constant load, especially if it's humid. It's almost like they get tired. Okay, so we understand the problem, it's the flaws, we know how to measure their effect and model it with statistics. Now for the payoff. How do we use all this knowledge to actually engineer ceramics that are stronger and way more reliable? This quote from the Handbook of Advanced Ceramics just nails it. It boils down the entire engineering strategy into 2 simple paths. Path number 1, perfect your manufacturing process to make those starting flaws as tiny as possible. Path number 2, accept that flaws will always exist, and instead engineer the material itself to be fundamentally tougher so it can just stop a crack in its tracks. And here's the playbook engineers use to follow those paths. First, everything starts with better raw materials. Using super pure, fine powders gets rid of a ton of problems right from the start. Second, you have to precisely control the firing process, what we call sintering, to get the part dense without letting the crystal grains get too big. Third, and this is related, you actively want to limit that grain growth, since finer grains usually mean a stronger part. And finally, you can get really clever and design the microstructure with built-in crack-stopping mechanisms. So the next time you see some high-performance ceramic part, remember that its incredible strength and reliability are no accident. It's the direct result of a deep understanding of these tiny flaws and decades of advanced science, all dedicated to controlling a material's structure at a level you can't even see. And that leaves us with one last, pretty fascinating question. We figured out that a ceramic's practical strength is all about its flaws. But what if you could make a truly perfect ceramic, one with no flaws at all? What's the limit then? Well, that's when you get down to the theoretical strength of the atomic bonds holding the material together. And pushing ever closer to that ultimate limit is what keeps material science so exciting.